Ready now to take up the idea of what a central potential is and what a central force is. But before we go on to the formal way of deriving or defining these quantities, one more example will not be out of place here. We have already seen the example of a gravitational potential due to a spherically symmetric mass distribution. The other example, the famous example, is in electrostatics, where Coulomb's law tells you that the electrostatic force between two charges, point charges q1 and q2, or little q and capital Q say, is of the following kind. So if you put one charge here, capital Q, at the origin of coordinates without loss of generality, here's x, y and z, and you put a test charge here, little q there, at some distance, little r, from the origin of coordinates, then the force on this test charge F on test charge, the electrostatic force, as you know, is capital Q multiplied by little q divided by 4 pi epsilon naught times r squared multiplied by the radius vector, or the unit radius vector, unit radial direction vector from the origin to this point here. So exactly as in the earlier case, we could ask, what's the potential? Well, actually this is the force, but the electrostatic field itself, E, at any point distant r from the origin, is not dependent, once again, because it's a point charge at the origin, spherically symmetric, it's not dependent on the spherical polar coordinates theta and phi. It's dependent only on r. So to indicate that, I write it as a function of r without putting in a theta or a phi there. This quantity is equal to q over 4 pi epsilon naught r squared E sub r. Okay. When you multiply it by the charge, the test charge, you get the force on the test charge, because we know the force is the charge times the field, the electric field. Now this thing here will imply that it's derivable from a potential phi of r, again a function only of little r. This is the electrostatic potential at any point distant little r from the center of from the origin. This is equal to q over 4 pi epsilon naught r, and there's no vector, it's a scalar. This quantity is a scalar, because now you see that if I differentiate d phi over dr and put a minus sign, this quantity is q over 4 pi epsilon naught r squared, and I multiply it by E sub r, and therefore this quantity can be written as minus d phi over dr E sub r. Here. So once again, I have a potential which goes like the gravitational potential, it goes like 1 over r. The fact that you have a plus sign here and you had a minus sign in the gravitational case had to do with the fact that when you have two masses, both of which are positive, the force of gravitation between them is always attractive, whereas if you have two charges which are like charges, both little and capital Q have the same sign, the force between them is repulsive, whereas in the case of unlike charges, charges of opposite sign, the force is attractive. So to take that into account, there is a little minus sign that appears or does not appear in the potential. But the functional dependence, the 1 over r dependence, is exactly the same as before. Now this is what the electrostatic potential is due to a single charge, and it again, now the statement is that any time you have, in general, you have a force which is derivable from a potential in this sense. In other words, whenever you have a force F which depends only on the radial distance at any point, if this is equal to minus d over dr phi of r times E sub r, if the force is equal to this, then phi of r is a central potential. Central in the sense that the corresponding field or force, its derivative, is directed in the radial direction, inwards or outwards, doesn't matter. No angular dependence. And the corresponding field is called, the corresponding force is called a central force. The potential is a central potential. Okay. So the two famous examples of central potentials are the gravitational potential due to a spherically symmetric mass distribution or a point mass at the origin, and a charge, an electrostatic charge. In each of these cases, if the distribution deviates from a spherically symmetric distribution, immediately you have a much more general kind of potential. It's no longer a central potential necessarily, because there is no spherical symmetry left in the problem. In fact, you can see immediately that if I have two charges, this goes away at once. This property is immediately lost, as you will see. If I have a charge Q1 here, let me call it capital Q1, at position R1, and a charge Q2 at position R2, and I ask what's the potential and electrostatic field at some point, arbitrary point P, whose position vector is R. How do I do that? I put a test charge here, unit positive charge, or a charge little q there, and ask what's the force on this charge due to these 2 points which are kept fixed. These two charges are assumed to be kept fixed at these locations. Well, the electrostatic potential phi now is a function of r theta as well as phi. So let me call it phi of r at this point. And just to show that it's at this point, I put in a little r here with a vector symbol to show that it changes from point to point, and I don't care where the origin is. Here's the axis, and that's at a distance little r from it, and these are at r1 and r2. This is equal to q1 over 4 pi epsilon naught times the distance between these 2 points, which is of course equal to modulus of r minus r1 plus q2 over 4 pi epsilon naught modulus of r minus r2. That's the gravitation, that's the electrostatic potential at this point. To find the field at that point, I need to differentiate it with respect to the coordinate r of that point. But this r and this r here, now all the various 3 coordinates r, theta and phi will all appear here when I write this expression down. It's not a function of little r alone. So in this case, the potential is not a central potential. It arose from 2 central potentials, but the 2 potentials have got superposed. And this is crucial. The forces or the fields at this point due to charge 1 and charge 2 vectorially add up to give the net field at this point. For instance, if this is positive, that's positive, and this test charge here Q is also positive, this exerts a force away, that exerts a force away in this direction, and there's some resultant field between the two, resultant force, which is the sum of these two, the vector sum of these 2 forces here. But this involves adding vectors, and when you have more and more sources, this addition becomes more and more cumbersome. On the other hand, the potential adds up. It's simply a scalar, so there's just algebraic addition of these numbers, and there's no vector here involved. The vector comes when you start differentiating with respect to the different coordinates here. In this case, it is not possible for me to write down the electric field at the point r. This is not equal to d phi over dr alone. Not true, because there's also dependence on theta and phi, on the polar coordinates of all the points concerned, including the point where this field is being measured here. There's a more general formula for it, which we will write down in suitable form later on, but right now the important thing to remember is that whatever be the force, it is still derivable from a potential. There exists a suitable potential from which you can find, with suitable differentiation with respect to the coordinates, you can find the field at this point. And the great advantage of using potentials as opposed to using the forces or fields themselves is that potentials are scalar quantities, and you add the scalar quantities from different sources, corresponding potentials, and then calculate the field once and for all by differentiation, rather than finding the fields due to each individual charge and then trying to add them up vectorially. That's much more intricate. So that's one great advantage of using the idea of a potential. Okay. So we've said something about a central potential, and the moment you have a central potential, it doesn't have to go like 1 over r or anything like that. Any function of little r alone is a central potential, and then you're guaranteed that the appropriate force or field is given by this formula here, exactly as I've written down here. And the important cases are spherically symmetric charge distributions, spherically symmetric mass distributions. They will lead correspondingly, because of Newton's law of gravitation and Coulomb's law respectively, they lead actually to forces which are central forces. Okay. Okay. There's another physical example of a central force which is very important. So we will go through that, I'll mention that, and then we will come back and look at the other advantage of using, or the other important property of a central force. Okay. And this has to do with intermolecular force. Okay. Now that's an intricate subject. The force between molecules in matter is actually quite complicated, because the molecules themselves are quite complicated, and it generally involves calculation of these forces from first principles, involves fairly intricate quantum mechanics, and is really very difficult in most cases except in the simplest instances. But we do know something, which is that in general there's a there's a standard qualitative way in which this force generally behaves under suitable conditions. So we look at the case of neutral molecules, essentially electrically neutral molecules, and with some degree of spherical symmetry. So once this spherical symmetry is present, then the intermolecular force looks like this, and it's a very typical graph. It's a central force. So what we have in mind is, at this origin of coordinates, putting one molecule at the origin of coordinates always. So one molecule is sitting at the origin of coordinates, and the other molecule is a distance r away from it. So we have in mind a situation where there is a molecule at the origin of coordinates here, and there is some other molecule here at a distance r from it. And the question is, what's the potential at that point, or what's the force on this molecule due to this molecule at a given distance r from it. So that's the typical question we'd like to answer, and it goes as follows. It turns out that this force looks very generally like this. This force F of r, again it's a central force, one of them has been put away at the origin. This central force goes like some quantity F of r times E sub r. Because it's central, it must be directed either along the line, it's always directed along the line joining these two points, molecules, either inwards or outwards, depending on whether the force is attractive or repulsive. So if F of r is positive, greater than 0, implies repulsive force, and if it's negative, it implies attractive force. And it turns out that in most cases this force becomes extremely large and repulsive, and then it becomes this kind of thing. So there's a point here where it changes sign, and to the left of that point, if I plot F of r here as a function of r, to the left of that point this force is repulsive. These two molecules repel each other, but to the right of that point, namely in this region here, the force is attractive and tapers off to 0, as you would physically expect when the distance between the two molecules becomes unbounded. Okay. Now can this be derived from a potential? And the answer is indeed yes. There is a minus dV over dr here, and the corresponding, so this thing here can be written in the form minus dV over dr Er, and the V of r itself has the following shape. At the point where this force is 0, since that force must come from minus dV over dr, it means V must have an extremum, and out here you can see that dV over dr, which is F, is tending towards infinity at this point with a minus sign. The slope here is negative, so this V of r must also tend to plus infinity at this point, and here is 0. So this force must look like this. Extending this point here, it must look like this. So there is some kind of minimum here where the slope is flat, and that is why F is 0, because this F is minus dV over dr. This quantity is equal to that here. So where it crosses, where the force crosses 0, you have equilibrium. There is no force, net force on the other molecule. The attraction and repulsion kind of cancel each other out, and this is a point of equilibrium. Not stable equilibrium, because if you displace it a little bit, it will move out, unless this thing here is a deep enough well. On the other hand, if you give it a sufficiently large displacement, you may dissociate these two molecules, but otherwise there could be oscillations about this minimum here, which we will talk about when we talk about oscillations. On the other hand, what happens at this point? The dV over dr in this entire region is repulsive, because the slope is negative minus the slope is positive, and that is what this F is doing up there, very steep, and on this side the slope is positive after the minimum, therefore minus the slope is negative, and the force is indeed negative here with a certain equilibrium point. So this is a point of equilibrium. Equilibrium point. So if there are no other effects and you manage to put these two molecules exactly this distance apart, this system will be in equilibrium, in stable equilibrium at this point. Of course, in a real substance there are thermal agitations and so on, so the particle actually they will move about, perhaps oscillate about this point of equilibrium, leading to a variety of interesting effects. Okay. Now what is this due to? What's this generic thing due to? And it's worth understanding a little bit where this force comes from. In the simplest instance, if you have two electrically neutral molecules, this means that there is, or atoms for that matter, there is a negatively charged electron cloud and there is a positive charge at the center, and similarly you have a negatively charged electron cloud and you have a positive charge in the center. And strictly speaking, if these are static objects, the electrostatic field outside this distribution at any point here is 0, because it's spherically symmetrical, and then the electric field, as you know, is as if the entire charge distribution was concentrated at the center. And if the object is electrically neutral, the total positive and negative charges cancel each other and give you no field here at all. On the other hand, these are dynamic objects, and what happens is fluctuations in the spherical symmetry of this distribution induce so-called electric dipoles, which in turn polarize this distribution, and so you have an interaction between a dipole and a dipole, which does not satisfy this property that the electric field outside is 0 or anything like that. It's not spherically symmetric anymore, and there's a net force between these two objects here. This force turns out to be an attractive force in most instances, and is in fact responsible for this part of the potential, namely the attractive force here. And this force typically dies down like a very large power of the distance between them. This force F of r tends to 0 typically like 1 over r to the power 7. 7 appears quite naturally, and therefore the potential goes like 1 over r to the power 6 typically. Later on when we do electricity and magnetism, I'll give an explanation, a very simple one, of why this particular power 6 should appear in the potential of all powers. On this side, however, when you bring them sufficiently close together, then the Pauli exclusion principle prevents you from having electrons, 2 electrons in the same state simultaneously, and this leads to a repulsion. That's largely responsible for this repulsive part of the force, and it in fact goes to infinity extremely rapidly. Typically this would go like 1 over r to the power 12 with a plus sign, and that with a minus sign because it's from below, and this is tending towards plus infinity with a 1 over r to the 12. So this kind of potential is often called a 612 potential. It's also called the Lennard-Jones potential. Between neutral atoms or neutral molecules which are roughly spherically symmetrical, and very typically, while the details in different cases differ, the shape of the potential and therefore the shape of this central force is more or less standard in this form. Now what this power is will depend on the details of the molecules, as will whatever happens here. That's easier to model, it turns out, than this. It's fairly complicated. Quantum effects are involved in trying to discover what the repulsive force is at very short distances, but this thing here is the generic shape of this potential, and it's a central potential. Therefore we can write down what the force is. It's a central force. In the first approximation, when this potential is valid, one actually has a way of modeling intermolecular forces and then proceeding to see what happens when you put a lot of them together to condense into some form of condensed matter like a liquid or a solid. So I thought I should mention this here because that's a crucial and very important application of the idea of a central potential. The many other applications of these central potentials, will come back to this as we go along. Meanwhile, for a conservative force, there is one very important property which is crucial, and that's as follows. I already mentioned that if you have a potential at every point, so here is r, here is r plus dr, say, and the force that's acting on your particle or object is f of r. This is equal to derived from a potential, so this is equal to minus d phi r over dr er for a central force. Then the work done in taking this particle from here to some point like this with respect to some origin, so let's draw this origin here. Here's the point r vector, and let's suppose you move to the point, some other point, some finite distance away. So let's move there to that point along some prescribed path. So I move in this fashion to this point here, which is, and let's start with r1 and I move to r2 in this fashion. So under the action of this force, this particle moves from r1 to r2, and the work done is equal to f at each point, f of r dot dr, and you must integrate or add up all these infinitesimal pieces. So here's the first displacement, the next displacement, the next, etc. These are all little infinitesimal dr vectors, and the vector sum of them will move you from one point to another, and the total is an integration from the point r1 to the point r2 in general. Now that's not a trivial integral to evaluate in general. On the other hand, when the force is a central force, then you can see that the force at this point is radially, let's say, outwards in this fashion, and the object moves here to this place here. The actual work done is the component of this displacement along this radial direction here. So it's only the radial portion that contributes, and that's not hard to write down, because once I write this as this form here, then you can see this is equal to an integral from r1 to r2, whatever be f of r we don't care, minus sign d phi only of the distance r over dr er dot dr, this fashion. But look at what happens to dr. We know in general that dr is equal to dr times the unit vector in the radial direction plus r d theta times the unit vector along the polar increasing polar angle direction plus r sine theta d azimuthal angle e phi, unit vector along the direction of increasing azimuthal angle. Now you have to take that and dot it with er, dot this equal to er dot this quantity. But er, e theta and e phi are at right angles to each other. They form a right-handed triad. So er dot e theta is 0, er dot e phi is 0, and therefore this reduces to dr times er dotted with er, which is equal to 1. So this is just dr, and therefore this reduces to minus the integral from the point r1 to the point r2 d phi r over dr times dr without any vector signs. And that's a simple integral to do, because this is minus phi at the point r2. But now this is a function only of the distance of any given point, and therefore it's only r2 without a vector symbol plus phi of r1, which is equal to phi of r1 minus phi of r2. So we have this beautiful property that the work done on the system by this force in moving from a point r1 to r2 is not dependent on the details of this path at all, but is only a difference equal to the difference, depends only on the potential, and it's the difference between the potential at the initial point minus the potential at the final point here. And in this case of the central potential, this is a function of only this distance little r1 and the distance r2 here. Therefore, if I took any other path, all that would be relevant would be in each infinitesimal displacement, what's the component of this force in the radial direction. That's all that's relevant, and it immediately leads to this answer here, phi of r1 minus phi of r2. So it immediately suggests that you could as well replace this path by a straight line path, and you'd get exactly the same answer. No matter what you do, what kind of path you do, the work done in going from here to here is independent of the path and depends only on the endpoints, which also says that if you come back in a closed loop, the total work done must be 0, because it's the difference between the potential at a given point and itself, which is of course identically 0. So we have this very important property that when you have a conservative force, well, we did this for a central force in this case, derived from a potential, but when you have a more general conservative force, the same property turns out to be true. That involves a suitable, writing down suitably a derivative here which is not dependent only on ER but also E theta and E phi, but we will see, we will show this later on, that even in that case it will be only a difference of the potentials at the initial and starting points. So the second important property of a conservative force, of which a central force from a central potential is a special case, is that the work done in a closed path is 0. The work done by this force on a system in a closed path is 0, or equivalently the work done in going from any point to any other point is independent of the actual path taken between the 2 points and dependent only on the potential difference between the 2 points. And that's tacitly, implicitly put in by us in elementary calculations whenever we compute the change in energy and so on by simply computing the potential difference, but it's based on the fact that in the case of a conservative force, the work done in a closed path is 0, or the work done in going from any point to any other point is a function only of the potential difference between the 2 points. And in the case of a central potential, it's particularly easy to demonstrate that this is so. We will see more examples of this property as we go along.